Jnanam paramam dheyam. Knowledge is supreme.
Hello students. Last lecture we looked at the simplest of the linear controllers, which was a proportional controller, and we saw that one of the main limitations of a proportional controller is that it is not able to reach, it is not able to give you the response which reaches the desired value or the set point value, and we always end up with offset which is non-zero, and in order to get the offset free response we have to increase the controller gain to mathematical infinity, which in reality is not possible. So, what we saw was that when we have a proportional controller, our u was, the deviation in u was proportional to the error or the current error. So, we are just looking at whatever is the instantaneous value of error, and the controller is taking action based on the current instant, and it is not looking at how the process has reached there. So, there is no contribution coming from the past history of the process, and that is resulting into this offset. So, in order to improve this performance, or rather I would say in order to get offset free response, what we do is we, along with the current value of error, we also get a term which is proportional to the integral of all the previous errors. So, what we do is, along with the current contribution, we also look at the past contributions or how the system has reached to that point, and the weighing factor for that is 1 over tau I. Will come to that significance of that in a bit. So, what we have is a controller which takes action which is proportional to the error as well as integral of the error. That is why it is known as a PI controller, and we will see how this addition of integral action is going to cause the offset to go to 0 even for finite values of proportional, even for the finite values of controller gain. So, this tau I is known as integral time constant, and in sense it is used to kind of trade off between how much contribution we want from the current error and how much contribution we want from the previous history of the process or past errors. So, a large value of tau I means more P than I. So, there will be more penalty, or the contribution of the output will be largely dependent on the current error and less on the history. When a small integral time constant is used, you will have more penalty on the integral term than the proportional term. And this time constant, it tells you. So, let us now look at how the addition of integral action, how it is going to respond in terms of a simple process, which let us take a first order delay process, a first order lag process. So, let us start with regulatory problem. So, we had seen that the regulatory transfer function is given between the output and the disturbance, and it is equal to GD over 1 plus GP, GC, GV and GM. In this case, we are looking at a first order process. So, let us say Gp is equal to Kp over tau s plus 1, and for simplicity we will also assume that Gd also has the same time constant. It is not necessary to have these two time constant to be the same, but it just simplifies the algebra. We will also assume that the measurement is instantaneous and the Wolff transfer function is also equal to 1. And then lastly, the controller we have used is a PI control, So the Laplace transform of that will be given by Kc 1 plus 1 over tau I, and the Laplace of integration is 1 over s. So the entire transfer function for this controller is Kc into bracket 1 plus 1 over tau I s. So let us see how does this regulatory response looks like. So which we can simplify, and then what we get is so eventually what we will get is so what we are getting as the regulatory response is a second order process. So we started with a first order process, and because of the integral action we have increased the order of the system. So if we try to connect to what we did during the dynamics module, what it is going to cause is it is going to cause the system, the closed loop system to respond sluggishly compared to the original system, as we are increasing the order of the system. But this disadvantage or limitation is coming at an advantage that we have a 0 at origin. So that is the main contribution of the integral action. This s is in the numerator is coming because of this additional integral action which we have done. And if you again recall to the numerator dynamics lecture, when we have a 0 at the origin, the whole this results in the response to go to 0. So irrespective of the amount of step change in D and irrespective of the value of Kc and tau I, as long as they are not 0 or infinite, what you would see that the 0 will of this transfer function will always occur at origin, and because of that the response, the yt, will always go to 0 as time goes to infinity. So what does that mean? Irrespective of all these things, even though a disturbance occurs, the response will always go to the desired value. So we have seen that with the addition of this integral action, we have been able to cause this offset to go to 0. And we will see that the same thing is true even for the servo problem. So PI control of first order process, and if you look at the servo problem, in that case the transfer function Gs is between the output and the set point, and it is equal to Gp Gc Gv over 1 plus Gp Gc Gv Gm, and again for this process we have Gp is equal to Kp over tau s plus 1, Gc is equal to Kc 1 plus 1 over tau is, Gm we have assumed to be 1, Gv we have assumed to be 1. So, in that case what we are going to get is as follows. So, ultimately what we are going to get is so this is the response or the transfer function between the set point and the final output. So, you can see that again it is second order. So, again the integral action has increased the order of system by 1. So, the system is going to be slower, but not entire, that statement is not entirely correct. The reason being we also have numerator dynamics. Which is of order 1. So, the net effective order of the system still is 2 minus 1 equal to 1. So, the system is still going to behave more like a first order system with initial non-zero slope, and if you look at the gain of this system. So, if I say the set point had a step change of magnitude A, and I am looking at where does the output reach as time goes to infinity, we will limit using the final value theorem. We will limit s tending to 0 g of s, which a times g of s, which is equal to a times the limit of that function which we have just derived, which is 1. So, what you get is the final value of the output is also same as whatever was the set point change which was given. So, this implies offset goes to 0 for finite value of controller gain. So, using both these regulatory mode as well as servo mode, what we have been able to see is that because of this addition of integral action, we have been able to move this offset to 0 even for finite values of controller gains. Now, before proceeding further, let me also make a comment on why do we always go with a PI control and not just I control. What if I had used only the integral action and no proportional action? In that case, we still get offset free response. So, if I say I control, so it does solve the problem of not getting any offset even for finite values of gain, controller gains. But if you look at what you would get as the servo transfer function, it will look something like this. So, I guess you are able to figure out what is the difference. It has no numerator dynamics. So, the implication of that is this is effective second order system, so which is slower than original system. So, if we use only the integral action or the penalty only on the past values, what we are going to end up is the system, the closed loop system becomes slower than the original process and the system does not respond that fast. So, if we want to compare these two responses, in one case so, if I use only I controller, the response, if it is underdamped, it will look like this. So, this is only I control. The addition of this P or the proportional action is going to make this response look like this. So, the system reaches the final set point much quicker compared to just the I control for the same values of integral time constant. So, that is the main reason why only integral action is never used, it is always used in conjunction with the P controller. Now, you can see that as we have a second order dynamics, this opens up lot of possibilities in terms of what kind of dynamics we might expect from closed loop system. And so, this closed loop system, either this or the PI control, what we can see that depending on the values of Kc, tau, tau I, so tau and Kp are fixed based on the process, but by choosing the values of Kc and tau I, we can always make this response either become overdamped, critically damped or underdamped. And most of the times what we end up doing, especially for servo type of problems, is that we look at and we try to make it as an underdamped response. The reason being, so let us say if we have, this is the set point which we are tracking. If we use overdamped response, the response will look like this. If we are looking at critically damped, it will be faster, and if it is, so in all these cases what we will have is the initial slope will be non-zero as we have numerator dynamics, and then if we have underdamped response, this is what we get. Now, the advantage of underdamped response is that the system reaches the neighborhood of the set point much quicker compared to any of these responses. So, this, let us say if this is the point at which it is reaching within this particular neighborhood of the final response, what we can see that the underdamped response is much faster to reach within that particular value. So, if let us take an example that it is some sort of production rate which we want to attain. So, initially we were operating at certain production rate and now we want to increase the production to this new value, then you would want to reach to within the neighborhood of that final value as quickly as possible, so that we start making lot of profit rather than having a very slow trajectory towards that final value. So, most of the times underdamped response will be desired. The only cases where we would not want to go with an underdamped response is when we have something like this set point is also close to the stability or the safety limit. If it is for example a reactor temperature which is getting controlled, and this final set point is also close to where the catalyst activity is maximum, and the catalyst may get degraded if we increase the temperature beyond that value. So, obviously, as we are going for some portion, we are already above the safety limit or the good temperature at which the catalyst can work. So, this temperature may be detrimental. To catalyst, for example, or it may cause some explosion or the safety limit. So, in that case such kind of oscillations or the overshoot may not be desired, and in such cases you may resort to critically damped response. But having a PI control gives you that flexibility that you can move from one type of dynamics to the other type of dynamics. So, what we have now seen is that by the addition of integral action, we have now a system which can reach its desired set point. The only and then what you should then see that PI controller should be present everywhere in the world, and there is no need for any additional thing. So, in fact, that is not the end of the world. There is always something which can improve the performance even from PI control, and that is the whole thing is the PI controller, even though it causes the offset to go to 0, but at the cost of some penalty. And that penalty is higher order dynamics, because we are increasing the order of the system by 1. So, it tends to slow down the closed loop response. So, in order to improve the speed of response, what we do is we add derivative action. So, we will talk about the effect of PID control after the break. Thank you.